Hi guys, it's a little late at night here. It's 12:15 on Friday the 13th of all days to try and talk about something like this. Anyway, there's something I like to riff on, even if I do not consider myself an expert, and that would be quantum computing. Okay, because by the way, my handle for AOL a long time has been Metaqubit, Metaqubit, based upon the idea that it will be a hierarchical organization of qubits. That may happen someday, but at the moment it's not obvious. And also the handle bioqubit, that is to say, biological qubits, an idea which is now beginning to see some expression. Okay. Meantime, though, the problem here is well, let me set it up this way. Whether they like to say it or not, the discussion about AI these days is undergirded by um yeah, hold on a second here, hold on, don't move. Yes, I had to turn off the tennis in the background, sorry. Okay, AI is undergirded by neural networks, which is driven by what are called matrices. Okay, repeated passing of values through a huge number of matrices. And the basic model you'll find is called counterpropagation as developed by Dr. Jeffrey Hinton. Now, that's fine. Let's just keep the idea of matrices or a matrix, okay, just a grid of numbers in mind. And if you go back to the very early days of quantum computing, the in the 90s, the concept of quantum computing was entirely theoretical. There was no physical basis for it. The mathematical modeling at the time in the late 90s arrived at the conclusion that yes, quantum computing would be feasible. And it was on the basis of those mathematical models that you had researchers developing the very first qubits or quantum bits to demonstrate that this could happen. And of course, it's been a struggle ever since, but there is the sense that we might be getting close to something that could be big. So it's interesting that they used matrix math in the beginning to decide that quantum computing was feasible, and that matrix math is the core of today's AI revolution, so-called revolution. Yeah, I'm not going to take away from the power of it, but it's curious that the way this would work. And yes, one other quick point is that there's a model developed by, oh God, he's an anesthesiologist at the Arizona State University. His name escapes me right now. But his model of consciousness also works off of a version of, it's actually a physical model of the proteins inside neurons, which would also follow the concept of a matrix, more akin to perhaps an abacus. But the point is that these point in a certain direction, if you will. Now, what does this mean for quantum computing? The problem I'm having, I can't resist. Sorry, another digression. Got to take it. So we recently had this demonstration of some researchers having taken 800 neurons in a dish, petri dish, if you will, and they were able to teach those 800 neurons to play a game of Doom, which I guess is a little bit like Pong. And I think that the other neurons, they've been able to demonstrate they can learn how to play Pong. This is bizarre, yes, but it's a warning, yes. And it says something about how the brain works. And I think part of this will bring us back to some questions about the relationship. It's a three-part relationship: quantum computing, artificial intelligence, and neurons, or quote, actual biological intelligence. And yeah, these seem to be moving in a certain direction, and they're converging. That's that direction. Okay. So I want to jump now to my question. If optical computing and the reliance on if, let's try that again. If quantum computing, not necessarily optical, has to um, rely on this concept of qubits, then we have to talk about quantum entanglement of photons. Now, this leads to my question then. Is there a neural equivalent to photonic entanglement? In other words, can you have, quote, entanglement in neurons that are akin to the kind of entanglement that's key to quantum computing? So I'm just going to say right now I'm asking the question. Um, we think of the brain as primarily electrochemical in nature, so we don't necessarily associate it with optical features. But you do have bits and pieces where there is a thing. It's called optogenetics, for example, and that uses optical technology to manipulate how neurons function. So there's some bridge there, but now are we going to find things? Oh, and also, I can't resist. Now I'm going to go back in further time. It was, again, a crude demonstration, but it goes back to the 90s where we were able to show that you could get cells to actual biological cells to actually laze like a laser. Okay, we've got to think about that one too. So there are bits and pieces of different areas of research over a long period of time, which, in my mind at least, can be cobbled together into some crude model of something that inspires a question like this. Is there a neural equivalent to photonic entanglement? So I will let this video be the one that raises the question, and the one that comes after it will try to get you some answers. So hopefully you'll be tuning in. Thanks a lot.